So we're going to begin this Uber for MBSE talk with a question. The question is, how many digital threads have you seen spanning a system's life cycle from stakeholder needs all the way through to supply chain management? Now, the reason why I ask about this is that there has been a proliferation of factors upsetting just about everybody's supply chain needs these days, right? From natural disasters, more recently pandemics. And as a result, everyone's having to redesign their products, manufacturing processes, and sourcing plans to accommodate these upsets. And yet, we don't hear much about digital threads being used to design more robust supply chains, or at least to rapidly redesign disrupted supply chains. Well, over a year ago, DARPA noticed the outage and funded a research program along these lines. And the participants of that program are shown here. And this brief is about that team's work and results. We'll cover that topic by starting with the problem space, moving the solution space, and then wrapping up with a pilot to add some context and to ground it. So moving on to the problem. The problem is basically that we have 1,300 strategic API, pharmaceutical ingredients, if you will, APIs, whose supply is at risk because one or more of the raw or intermediate materials in their manufacturing process trace back to high-risk regions or countries. The candidate domestic manufacturers are well known, and the synthesis pathways are known because they're off patent, at least at a high level. But it is a monumental task to reverse engineer and manually document all the equipment requirements for hundreds of API. And it's an equally monumental task to get dozens of suppliers to work with dozens of sites to confirm their ability to provide equipment that can comply with thousands of specifications. It's no wonder that we still have so many API at risk. Somewhere along the line, the program team recognized the similarities between our program and the solution spaces of that of Uber. The similarities were inspiring because, Uber, of course, totally transformed the space that they live in. And it caused us to envision a bigger transformation for our space. And we'll see how much of that we achieved as we go through here. We'll see what you think. But in addition, it did prove to be a useful analogy to help people understand what we were doing. And let's see if you agree as we go through the presentation. In any case, to get started on the analogy here, Uber's mission is to find transportation solutions in a rapidly changing environment in a way that benefits both buyers and suppliers by automatically aligning requirements from the buyers with the capability of the suppliers. In the case of an API supply chain, we really only have to change one word to have this make sense. We go from transport to manufacturing and it works from a mission standpoint. And when it comes to the buyer-supplier interactions, that fits pretty good too. And in fact, it's kind of odd how, in fact, both of these scenarios is about routes. One of them is synthetic chemistry routes and the other is about transportation. And there's multiple ways to get to the objective in both cases. However, the analogy does break down though when one considers that in the AP case, if you choose a different synthetic route, the equipment changes and how it's connected up. Whereas that's obviously not true in transportation. You don't change vehicles depending on the route you're going to. So, clearly the API supply chain scenario is more complex because it requires additional layers of requirements analysis. And no surprise that these additional layers of requirements analysis look a lot like doing model-based engineering of any system. And in this case, like most systems, the top layer contains constraints in the forms of manufacturing objectives that are then decomposed and mapped to the transformations upon which they depend. And then the transformations are in turn decomposed and mapped to the types of things that actually have the capabilities to do those transformations. And if we go further, we see that things look very similar again because we're dealing with instances of equipment that have to be described, functionally described, and then committed to use. So probably that's enough in terms of building the analogy there, and hopefully that got you on the same page, at least what we were trying to do with this project. And so let's move now a little bit more into the solution space here and take a look at a formal minimalistic solution paradigm. So if we take this problem space that we defined here and map it, the first thing we do is replace objectives with a way to formally declare the stakeholders that are allowed to establish the measures of success for the systems of interest. And then for the transformations, we have subsystems that represent the decomposition of the systems into the transformations that can be ultimately correlated back to the feature measures that we're talking about. And then we add behavior and constraints to guide the selection of physical archetypes that we use to perform the transformations. And then lastly, we just sort of rebrand the instance of things as asset registry. It's still tracking specific instance of things, but it more reflects the use of these things, that they really are assets. Just a couple of words about this asset registry, though. We were surprised at the lean-in from manufacturers, and we'll talk more about that in a slide or two. But we ended up documenting nearly 15,000 pieces of equipment, and this was like over less than 4 months, spanning 35 sites that were owned by 20 contract manufacturers. So don't be surprised if you try this in your arena and suppliers are anxious to engage and get their capabilities known. At any rate, let's set the meta model here aside and spend a moment contemplating the activity system associated with this meta model. So, here's the Uber template, but of course we're going to have to extend that because we have a little bit more complicated scenario going on here. So I dubbed this Uber manufacturing. And the first thing we'd notice here is that we have some needs processes where we define the system features, system requirements, and subsystem archetypes. And if you look at these collectively, they really look like a model-based RFP, RFQ. Now, running in parallel with this are the supplier processes, completely independent. They're going to do them regardless if the needs are there. They're going to identify what's their capability objectives, what business are they in, what types of transformations are they going to do, and then they buy assets according to that. But this Uber manufacturing scenario calls upon them to expose those assets, and you see the kind of orange color at the top of that asset archetype shape. It's meant to suggest that they're defining that in a way that complies with this overall Uber manufacturing standard. And of course, that's important because for this model-based application to be used by either the buyer or the supplier, it needs to have a common language here. And so this allocation functionality can read the requirements from the buyer and the capabilities from the supplier, and it can produce manufacturing solutions. And these manufacturing solutions are direct, fast feedback to the stakeholders that are making this whole thing run. And in fact, it's interesting here, right? Because we have exposed the assets in a way that's out there in the open and standard, and we've exposed the requirements for what needs to be produced, right? Both of these are exposed to the allocation engine. That means the buyer can execute this without putting any load on the supplier, and the reverse can happen. In fact, one of the suppliers that was giving us their equipment information asked us, they just sort of thought out loud and said, boy, I think this thing can tell me what equipment I need to buy to manufacture and grow my business in terms of the chemicals I'm producing. And so it helps them get an idea on the return on investment for capital investments to grow their business. So if you look at this thing, though, through the lens of ISO 15288, really it's about the life cycle of a system that is the supply chain, right? And it just looks a little different here because it's executing very quickly over and over again for 1,300 molecules that are refreshed every 2 years, probably even more frequently every time something happens, right? Or you might just run it in the background as an agent, right? Running, constantly looking at something change that can put me in a better situation from the supply chain. And it's basically held together like by the gravity of this very minimalistic meta model. So that's probably enough pontification about the activity system. Let's move on to the pilot context and get a better understanding of how the Uber-like model-based solution works. So, at a high level, if we're looking at the top of the meta model or the V, pretty straightforward. The types of things you're going to be looking for out of this solution and what we designed it to do was to be able to enter things like I need this many kilograms over this amount of time. You can't produce it in these regions. We're trying to manage risk. I want to minimize the cost, and maybe I want to also, I don't want to go to a single site or a single supplier. I want to force some diversity there. So there's typical, probably no surprise in terms of what the stakeholder requirements needs to be. When we start scooting down the V a little bit more in the meta model, a little bit more, the highest level decisions that you make when you're doing this model is what synthetic path am I going to do? And so that the choices that are made there as you go down the modeling path ultimately ends up with a decomposition of the path that you chose. And if we just sort of double click on that for a little bit and think about going from system requirements into architecture, basically what we're doing is decomposing. In this case, the lines is where it all happens, right? The molecules take most of the space on one of these routes, but the lines end up translating into thousands of blocks. But as we decompose those lines, we are and should end up running into patterns that are repeatable, right? Because it's chemistry at the end. There's kind of a fixed set of things you can do. And so we're just showing a sampling here of like standardized transformations, if you will, or functional archetypes. On the right-hand side, there's liquid containment, as simple as it gets. On the left-hand side, a little more complicated temperature managed reaction with condensation. And so if we just, to kind of make the point here around the knowledge that can be behind these patterns, we're just going to look at this temperature managed reaction and, specifically the temperature management part of it, not the reaction piece, and double click on that. And what we see is that there's a fair amount of knowledge in here just to do temperature management in a fluid context. And so I think the key point to take away from here is that these patterns are really not just about drawing, getting the model pulled together quickly, from a tactical perspective, but they really have a heck of a lot of knowledge in there. And so you can literally get your models built probably 10x, 20x faster. That's at least what we saw in our pilot than trying to do this as a one-off type of thing. And it really wasn't hard to identify those archetypes. I think it would be a natural for any other discipline or any other domain. So moving further down the V here, as we transition from functional to physical archetypes, we leverage an approach of mapping functional archetypes to the physical archetypes in the pattern library. I know you can't see that so clear here. You'll see that in a couple of slides, but take my word for it. The benefit of this approach is that as the modeler models the phenomena, that they are also laying the groundwork for a later automated allocation capability that will go through and find the equipment instances that can play these roles of these orange colored physical archetypes. And we're going to talk more about this in a slide or two. However, as you look at this, note also that allocation can be a little bit tricky, right? So there could be various types of equipment that you can allocate to do a particular function. So if I think about the temperature managed reaction, I could have a more sophisticated piece of equipment that's a reactor with an embedded heat exchanger in it, or I could go with two simpler pieces of equipment that I'm going to team up together. So a heat exchanger and a stirred tank reactor. Both of those are viable options, right, for performing a temperature managed reaction, and there's good reasons for both. And the idea is that as people are using this pattern to build a model, they're building that case in the background that the automation is going to need to actually search out through those orange physical stereotypes and find equipment down in the gray asset database there. So one last point on the modeling of chemical systems. I think it's probably true of any system. It's easy to underestimate the complexity, but our simplest synthesis is atropine, and that model is over 5,000 nodes and edges. So I think we can't overemphasize the value of patterns and knowledge, not just for efficiency of the modeling tasks, but also making sure we don't overlook knowledge and we can avoid some errors by just doing it once. So pulling it all together, we've repeated over and over again that the pattern library is the key to making all this work, and that we build a model from functional archetypes. And that's how we build the systems model. And we talked about the need for representing all typical configurations of equipment. And this is where you get your payback. If you don't put enough energy in it, you're not going to get as much out of it. But if you really spend the time to figure out what are the repeatable physical archetypes, what we do is we map these things to the logical system. And I haven't set it up until now. I've just sort of shown lines between them, but we use this concept called allocation permutation objects. And that's pretty important, and we'll get into that in a couple minutes more. But basically, they preserve the same functionality that we've been talking about all along here, where you can have different ways of configuring physical equipment to meet a functional need. And we had already talked here a slide ago about the heat exchanger and being able to, with the reactor with heat exchanger, be able to supply that as parts. And I just wanted to show these things in the pattern library so you could see them all right there and get a feel for, like, architecturally what this solution looks like. And I think we called it out earlier that these physical archetypes, they dictate the asset registry. Whatever fields are put in there automatically goes into the asset registry, and that's the information that is flagged for capture from the suppliers. So, however, there's a couple things that I didn't mention here. I didn't mention the role that allocation constraints play in terms of organizing the mappings between physical systems, logical systems, and the fitness scoring calculations that indicate the degree to which a functional archetype meets the needs of a particular an instance of a functional archetype, a physical archetype to a functional. Second, it's worth noting that if the fitness scoring involves something a little more tricky, like the execution of a simulation, this solution is built with an awareness of things like Model Center and Model Lines Impact Server so that it can outsource the execution of those fitness scores. In fact, we're using both on the pilot. Okay, so at this point, I think we're ready to do a walkthrough of an orchestrated use of all this stuff to actually produce some value. Up until now, it's all been like setting up the models. So we begin by opening up a manufacturing systems model for the product of interest. So one product, one model. And then we trigger the automation. And the system cruises through the model, navigating from each instance of a functional archetype back to its definition in the pattern library. And from that functional archetype in the library, the automation finds a potential permutation and navigates down through it to understand how to interrogate the asset registry to find all the instances of that particular physical archetype and to get the attributes of the same. Then for each piece of equipment it finds in there, it executes an allocation fitness test and it gets a result. If the result is a passing score, the automation creates a proxy object that references the equipment and also references the instance of the functional archetype for which it was determined to be fit for use. This pattern of analysis is executed for each permutation in the pattern for that functional archetype. And then it moves on, looking for the next element in the manufacturing model, tracing it back to the pattern, et cetera. So it does this, and ultimately it ends up finding all the equipment that can meet the needs of all the roles in the systems model. And then this permutation engine kicks into gear, and it starts taking different permutations of all these assets across all the roles in the systems model. And for each snapshot of that, it executes the emergent calculations that roll up to what are the things we talked about like 3 slides ago. What do we care about in this system? And it does that, saves those results for all the different permutations, and it ranks those based on a weighted performance of the different feature attributes specified for this manufacturing solution. And there you have your answer. So in summary, what you've seen here is a pattern-based modeling facility here where the patterns are really geared towards manufacturing, but it's not hard to imagine them in any context. We've talked about an asset registry, very similar to the Uber type of thing, and a computational simulation type of capability that are all pulled together to support an engine that looks for solutions. And you maybe don't think about this just as manufacturing. It may be that I'm just trying to formulate something. And so instead of having equipment, I've got molecules, and those molecules have stereotypes to us, which is physical archetypes. And I might want to crank through a number of permutations of different molecules that I might come up with for a formulation. So it's really an abstract capability that leverages automated allocation to produce insights. And in today's world where we have more and more devices, more and more molecules, it's going to be more and more relevant. So where are we going with this? A new company has been formed to commercialize the solution. It's called Occam Systems Incorporated. And we're initially focused on the chemistry. We want to follow through on that and deliver the value equations, working with a number of private companies. But in parallel with that, we want to verify that this thing works in assembled products, et cetera. It wouldn't be an accident because from day one and all the way through, we have realized in an abstract sense, it's the same problem for manufacturing anything. It's just that the patterns are going to be different, right? The functional archetypes, but everything else is the same. So that's where we are. And I'd be happy to take any questions you have.